Cartesian vectors. When we are working with the 3D problems, those 3D problems are simplified if they are represented into Cartesian vector form. The Cartesian vector form follow what is called the right-handed coordinate systems and the rectangular coordinate systems. Both of them, right-handed coordinate systems and the rectangular coordinate systems, are true if and only if that the positive z-axis here is directed or pointing towards your thumb. The y-axis is pointing towards your arm. Finally, the x-axis is coming out of your hand. In here, when that's a 3D diagram representing vector A. This rectangular component of vector A, we may have 1, 2, or 3 components. One component along the x-axis, another along the y-axis, and finally along one component along the z-axis. If and only if, as what you see in this case, if the vector A is directed or within an octant of the x, y, and z frame or x, y, and z axis. Therefore, by two successive applications of the parallelogram law, we may resolve that vector into components. The components of it, we know that, look at here, at the vector A, we can say A is equal to A dash plus AZ itself. A dash, the coming from the origin towards the A, plus the AZ. We know that from AZ to A is equal to from the origin to A dash, and that's why we're saying A is equal to A dash plus AZ. And then A dash itself has got two components along the X and Y axis. Therefore, A dash is equal to AX plus AY. When we combine these two together, combining A equal to A dash plus AZ and A dash equal to AX plus AY, combining both of them together, we will get A is equal to AX plus AY plus AZ. But also we shouldn't forget the unit vector. The unit vector along the x-axis it's I, along the y-axis it is j, and along the z-axis it is k. This unit vector has got a magnitude of 1 and it is dimensionless. Therefore, is the same equations in here or the same expressions in here, we take it as a is equal, or we express it in the form a is equal to ax I plus ayj plus azk. Now, finding the magnitude of that Cartesian vector. The Cartesian vector in this case, to find the magnitude, we know that already, taking the square root or the Pythagorean theorem, applying it because it's a right angle triangles we are dealing with. Therefore, is the same two equations exactly, or the same two formulas. A is equal to az plus a dash, and a dash is equal to ax plus ay. We will just take the square root of both of them. A will represent the square root of a dash square plus az square. Same thing with the a dash in here is equal to the square root of ax square plus ay square. Again, combining both of them together, same way we combine the equation in there, we will get, when we got here a is equal to axi plus ayj plus azk. Therefore, a equal to the ax square plus ay square plus az square. Now, if that's the case, how are we going to find the direction angle? The direction angle for each component is going to be alpha for the z-axis, beta for the y-axis, gamma for the z-axis, and we take the cosine of it. The cosine of alpha, of course, is equal to ax, the directions in here, the adjacent, over the hypotenuse, which is the ax over a. Same thing with cos beta and cos gamma. Now, if we were to form a full unit vector, and we know that a is equal to axi plus ayj plus azk, therefore that unit vector is got a we know that it's got a magnitude of 1 and dimensionless. If we were to divide the whole equation in here, or the whole formula that we have in here, by that unit vector a, therefore unit vector a is equal to a over a plus axi over a plus ayj over a plus az k over a, because it has got here a magnitude of 1. Therefore a over a, it is 1. We haven't changed anything. This is the directional angles in here: cos alpha, cos beta, and cos gamma. If we compare the unit vector formula in here with the direction angle formula, both of them, we will realize that ax over a itself, it is cos alpha, and ay over a itself is cos beta, and az over a itself is cos gamma. Now we substitute these into that unit vector formula and we get cos alpha I plus cos alpha I plus cos beta j plus cos gamma k. This is the substitution of these angles inside into the unit vector formula, but the magnitude of it's the square root of the sum of all of them. Therefore we can deduct that, or we can say cos square alpha plus cos square beta plus cos square gamma, it is equal to 1, which is the magnitude vector is equal to 1, and this will be the resultant of it. Okay, now if we were to add or subtract these Cartesian vectors in there, we know that looking at this here, this diagram or this figure in here, we have a resultant force R, and we know that R is equal to A plus B, but A itself can be expressed still into three components: X, Y, and Z components. So A is expressed itself on AX on the I directions, AYJ directions, AZK directions, and we will do the same thing for B. Now when we add both of them together, of course we collect like terms: AX plus BX on the I directions, AY plus BY on the J direction, AZ plus BZ on the K directions. And if and only if we were to subtract, we will do exactly the same. We collect again and subtract like terms from each other. That will result the resultant vector in here itself is equal to a plus b, and a plus b is equal to the expression here you see in front of you. Therefore we can deduct from all of this, and we say that the resultant force, or which is the vector r in here in this case, is equal to the sum of all of the forces, on x, y, and z axis. That means the sum of the forces on the x-axis, sum of the forces on the y-axis, and the sum of the forces on the z-axis. And of course, since we are expressing it in a Cartesian vector form, we have to add the unit vector I, j, and k. We'll see you guys in the next video for more practical problems to solve.